Hello everyone. Today we're going to do problem 13.52 from Fundamentals of Heat and Mass Transfer by Bergman and Levine. The problem reads as follows. It says an electronic device dissipating 50 watts is attached to the inner surface of an isothermal cubical container that is 120 millimeters on a side. The container is located in the much larger service bay of the space shuttle, which is evacuated and whose walls are at 150 degrees Kelvin. If the outer surface of the container has an emissivity of 0.8 and the thermal resistance between the surface and the device is 0.1 Kelvin per watt, what are the temperatures of the surface and the device? All surfaces of the container may be assumed to exchange radiation with the service bay, and the heat transfer through the container restraint may be neglected. So looking at our knowns, we're told that Q12, or the wattage, is 50 watts. We know that the length of each side of the cubical container is 120 millimeters. The temperature of the wall of the space shuttle is 150 degrees Kelvin, and the emissivity of the container is 0.8. We're also given the thermal contact resistance between the device and the container, which is 0.1 degrees Kelvin per watt. So the two things we want to find is the surface temperature of the container as well as the temperature of the device inside the container. So our schematic looks like this. We have our 50 watt powered device, which is attached on the inside of this container. Between the device and the container, we have a thermal contact resistance of 0.1. We know that the outside of the container has an emissivity value of 0.8, and we're asked to find the temperature of the container. The container, as well as the device inside the container, are all in this much larger volume of the space shuttle, and we know that the T wall, or the T of the bay, is about 150 degrees Kelvin. So some assumptions we're going to make, we're going to assume it's steady state, we're going to assume constant properties, we're going to assume it's a small object in a large enclosure, we're going to neglect the heat transfer through the container, so no conduction resistance from the container, and we're also going to assume that radiation from all surfaces of the container is radiating out equally to the walls of the space shuttle. So for our calculation, we're going to start by calculating the area of our cubical container, and that's just going to be 6 times L, which is the length of one side of the cube, squared. That's going to give us about 0.0864 meters. We can then go ahead and use this equation. So Q, the power, or the heat flux between one surface to the other, is going to be sigma, or the Stefan-Boltzmann constant, times area of the container, times the emissivity of the surface of the container, and then we're going to have T bay to the fourth, so the outside of the walls, or the bay, minus temperature of the surface to the fourth. So we can go ahead and plug in our numbers that were given. So 50 watts for the power of the device, Stefan-Boltzmann constant, our area, emissivity, as well as the temperature that we're given of the bay. And we can rearrange that for TS to the fourth, which will give us this value. And simply taking this value and raising it to the 1/4 power will give us our final answer, which is that the surface of the container is approximately 339.37 degrees Kelvin. So to find the temperature of the device, since it's only conduction that we're really worried about, we can use the simple equation of Q is equal to TD, which is the temperature of the device, minus TS, over RTH. In this case, our thermal resistance is our only resistance, so we could also take this as the total resistance. And simply plugging in the numbers we have, we know it's 50 watts generated by the device. We know that our surface temperature is 339.37 degrees Kelvin, and we know that our thermal contact resistance is 0.1 Kelvin per watt. And we can go ahead and rearrange, solve for TD, and we'll get the temperature of the device to be about 5 degrees hotter than the surface of the container, so about 344.37 degrees Kelvin.